Chemistry 1, we've done all this already. But I'm going to review how we did it in Chem 1, and then I'm going to teach you another way that will lead into 2.6. So Lewis structures have been developed to help us see the arrangement of the electrons in the molecules from the atoms that brought them to the molecule. So from experiment, chemists have learned that the most important requirement for the formation of a stable compound is that all of the atoms involved achieve noble gas electron configurations, meaning they are very stable, because noble gases are the most stable of all the elements. When writing Lewis structures, the rule is that only the valence electrons are included. So remember, we started a lot of times with the dot structure, right? So this, for an ionic compound, we have potassium, bromine, and bromine. So the valence electrons are the column number for a short way to think about them, but they do come from the electron configuration. So we have that. Now, we didn't really do ionic compounds that much in Chem 1, but for ionic, that means that they're transferring electrons. So the potassium will give its electron to the bromine, which is where we get this structure. And anytime that you have a charge around dots, then you put the symbol in brackets like that is. And we also do that for polyatomic ions too, with their Lewis structures. So that's how you do an ionic compound. For a covalently bonded compound, it's a little different. We have the duet rule and the octet rule. The duet rule shows that when hydrogen forms stable molecules, it only has one pair of shared electrons. Okay, so that means that its maximum that it can hold is 2 electrons, which is like helium. So even though it's only 2 electrons, it's still acting like a noble gas, helium, that has 2 electrons. So anytime that you bond up hydrogen one time, the hydrogen is done. Okay? The rest of the molecules, or the rest of the atoms in the molecules, want to follow the octet rule, which means that it needs 8 electrons, octet for 8, to fill the S and the P to be like the noble gases, and that comes from the electron configuration. Okay, so to do this, you want to sum up all of the valence electrons from all the atoms. We did this in Chemistry 1 just to check ourselves, to make sure we were doing it right. The way that I taught you in Chem 1, you will most often draw it correctly, but I'm going to also walk you through how to do the other way. Use a pair of electrons to form a bond between each pair of bonded atoms, and then arrange the remaining electrons to satisfy the rules. Sometimes the octet rule can be broken, but usually that's only broken on the central atom, never the branching atom. So the central atom is the only one that can break the octet rule or the duet rule. The rest of the atoms that are branching out from the central should still follow the rule. Okay, so let's draw some Lewis structures. The first one we have is HF. So we know that hydrogen contributes 1 valence and fluorine contributes 7. So that means that we need a total of 8 electrons when we're doing it. Okay, so in Chem 1, what we would do is we would draw each dot structure where we give each atom its valence electrons. And then from there, we'd start making our bonds. We'd connect things together until the octet rule was satisfied. So we know to bond the H to the F. From there, we have 8 total electrons because 2 from the bond, 4, 6, 8. Okay? So that's it for HF. And that is also a polar molecule because all the electrons are on one side. But let's try it differently for NH3. Okay? So each nitrogen contributes 5, and we have 3 times the 1 from each hydrogen. So we need a total of 8 valence electrons. Now, before, in Chem 1, I would teach you, okay, if you have just one of an atom, that's going to be your central. But now you can kind of look at electronegativity to help you decide what will go in the middle. And in this case, the nitrogen is more electronegative, so that would make it in the central. If you also thought of it as, oh, there's only one nitrogen, so that's got to be where everything else goes, that is fine. Okay, so now let's just draw our nitrogen in the center, and then let's go ahead and put 3 H's around it without even drawing dots. Okay, now we know everything has to connect to the central, so I'm going to go ahead and just draw bonds in between my 3 hydrogens and the nitrogen. So currently, right now in my picture, I have 6 electrons because of the 3 bonds, but I need a total of 8. So we have to add unshared pair, one unshared pair, and it will get added to the nitrogen, not to the hydrogen, because the hydrogen is already happy with the do-what rule. So we would add our 2 extra electrons onto the nitrogen. You would probably still get the same structure had you drawn it the way we did last year. Okay, it just doing it without drawing all the dots kind of makes your dot structure look a little bit nicer as you go. Okay, last one we have is the NO with the +1 charge. So nitrogen contributes 5, oxygen contributes 6, and then the +1 means we get rid of 1. So that means we need a total of 10 electrons when we're done. Now nitrogen, there's no central, okay, so I just went ahead and did that. So then now we can create a bond between the 2 of them. So that's 2, we need 8 more electrons. And so you might see like, oh, I could put 2 pairs on nitrogen and 2 pairs on oxygen. And so by doing that, we have 2, 4, 6, 8, 10 electrons. And last but not least, we would need to put it in brackets, show the charge, so that we lost an electron. Now, this is how some people came up with this in class. Personally, this is also correct. This is what I did. So I had my nitrogen and my oxygen. I like to double bond things if possible, so I created a double bond. And then the oxygen is more electronegative, so I gave that one 2 pairs versus just 1 unshared pair on the nitrogen. And there's still a total of 10 electrons, so this would also be a correct option for the Lewis structure of NO+. Okay, now some people get confused about like, why am I putting the unshared pairs over like that? Why am I not putting them on the sides of the box? We're going to get into tomorrow and the next day why we want to limit the electron pair repulsion. So we want to make sure everything is equidistant, and it has to do with bond angles, and we're going to talk about those angles later on. Okay, so now we're going to draw something where we break the octet rule. So BF3, each boron contributes 3, and each fluorine contributes 7, so that's a grand total of 24 electrons when we're done. Okay, so I know my boron's going to be in the middle because there's only one of them, right? Now let's try to make this more like a little prettier, right? So instead of just drawing 3 dots on boron, let's try to make the fluorines separate from each other. Like if you were cutting a pizza into thirds, you don't want to have somebody else get half of a pizza and you only get a fourth of a pizza. Everybody should get the same amount of the pizza. So by distributing your fluorines evenly, that will help make a nice distributed molecule. And then every fluorine will get 3 unshared pairs so that we can get our total of 24 electrons. So this is breaking the rule because the boron only has 6 electrons around it compared to the normal 8, but that's okay because we have paired up as much as we can. The octet rule mainly needs to be followed by the branching atoms, so the fluorines are all following the rule, so that's why that's okay. All right, and last but not least, let's do the xenon structure. So each xenon has 8 plus 3 times 6 for each oxygen gives a grand total of 26 electrons. Okay, we're going to have xenon in the middle because we have 3 oxygens to connect. Now what I did was I bonded twice. Remember I said I like double bonds, each oxygen, because xenon has a ton of contributing valence electrons. It's got 8. And then each oxygen would get 2 more pairs of electrons on them. Okay? But at this point, that's not enough electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We need to add 2 more on the xenon to complete that. So the xenon is breaking the rule, but the oxygens are not. So that's why this is okay. Now tomorrow, you might have drawn this a little differently. And tomorrow we're going to talk about resonance and formal charges and why your structure might be better than my structure or vice versa. But technically, either one is simple, or either one is right, but we like to accept